In today's lesson, we're going to be talking about the end behaviors of functions. So the end behaviors of a function, how it's defined to be, it's defined to be where the function is approaching as x goes to either x is tending towards positive infinity or x is tending towards negative infinity. And what we want to find out is where does that function approach the output. So in this case here, essentially we want to find the outer bounds of the function. So as x gets really, really large, where does the function f at x tend towards? And as x gets very, very small, i.e. approaches negative infinity, where does that function tend towards? These are called the end behaviors of our function. Let's look at some examples to illustrate this definition. So we've got the following degree 3 polynomial here, and you can see here as x is tending towards positive infinity, our polynomial is tending towards negative infinity. So again, as the x gets infinitely large, our polynomial in this case is tending towards negative infinity. Let's take a look at the other direction. Well, going in the other direction, as x tends towards negative infinity, i.e. it gets infinitely small, the polynomial, y in this case, is tending towards positive infinity. So in this situation here, we would say that the polynomial, negative x cubed plus 2x squared minus x minus 1, has end behaviors of negative infinity and positive infinity. One which tends towards negative infinity as x gets infinitely large, and the other tends towards positive infinity as x gets infinitely small. Let's take a look at some more examples. So some more common functions regarding their end behaviors, one would be y equals x squared. You can see here that as x tends towards positive infinity, the polynomial is tending towards positive infinity, and as x tends towards negative infinity, the polynomial x squared is tending towards positive infinity as well. So now let's take a look at y equals x cubed. For y equals x cubed here, we can see that as x tends towards positive infinity, our polynomial is tending towards positive infinity, and as x tends towards negative infinity, our polynomial is tending towards negative infinity. All right, let's look at some more examples. So again, these are two common examples. You've got your square root function, which as you know looks something like this, and you can see already the function doesn't exist when x is less than 0, so it has no end behavior as x approaches negative infinity because it's undefined there. But as x gets infinitely large, your square root function will continue on towards positive infinity. Notice for number 4 here, we have our reciprocal function. Notice here, as x gets infinitely large, your reciprocal function is tending towards 0. And as x gets infinitely small, your reciprocal function is also tending towards 0. Let's take a look at some more examples. So we have our exponential growth and decay functions here. You'll notice here y equals 2 to the x would look something like this. And for this one here, we have y equals 1/2 to the x, which will look something like this. So you can see here as x gets infinitely large, 2 to the x is approaching positive infinity. And as x gets infinitely small, we're approaching 0. On the other hand, you have the opposite situation for this side here. As x gets infinitely large, the 1/2 to the x is approaching 0. And as x gets infinitely small, 1/2 to the power of x is approaching positive infinity. All right, I'm just summarizing those two facts below here. Now, not all expressions have end behaviors. Let's take a look at an example. So periodic functions do not have end behaviors. The reason for that is obviously the function is always changing from, in this case here, we have our sine function will be one periodic function. You notice here this hits a max of 1, a min of -1, a max of 1. So we can see here as x tends towards positive infinity or negative infinity, our cyclic function or our periodic function is undefined. We are not approaching a finite value, or we're not approaching positive infinity or negative infinity. So this is an example of a periodic function that has no end behaviors. The next thing we want to look at is how do you find the end behaviors of random polynomials of higher order? The term that is of interest is the highest power. So in this case here, 2x to the power of 3 is what we want to do. So as x tends towards positive infinity, we can see here that x cubed will tend towards positive infinity, and therefore twice that will also tend towards positive infinity. So therefore p at x will approach positive infinity as x approaches positive infinity. Now as x gets infinitely small and approaches negative infinity, we know that when you cube a negative number, it's still negative. And then if I multiply by 2, it's still negative. So therefore my polynomial in this case here will approach negative infinity. So therefore the polynomial p at x has end behaviors of positive infinity and negative infinity. Positive infinity will happen as x gets infinitely large, and negative infinity will happen as x gets infinitely small. All right, let's look at the next one. So again, to discover the end behaviors of these polynomials, you find the highest degree. So in this case here, again, we're at a 3. But now notice, as x tends towards positive infinity, you'll see here, obviously, x cubed is positive, but then we're multiplying by -2, and in which case then our polynomial will tend towards negative infinity. So now notice if x tends towards negative infinity, x cubed will tend towards negative infinity, and multiplying by minus 2 will now make the polynomial tend towards positive infinity. Let's look at the next example. So for this example here, again, you want the highest power, so we're going to grab 4x to the power of 6. And you'll notice here as x gets infinitely large, x to the power of 6 will still be positive, and multiplying by 4 will still be positive. So therefore, 4x to the power of 6 is tending towards positive infinity as x tends towards positive infinity. And you'll notice here as x gets infinitely small, raising that to the power of 6 will make it infinitely large, and multiplying by a positive value will also make the polynomial tend towards positive infinity. Okay, taking a look at the last one here, again, grabbing that largest degree, we will have, as x gets infinitely large or infinitely small, in both situations, that polynomial will tend towards negative infinity. All right, let's take a look at some observations. All right, make some observations. If the degree of the polynomial p at x in this case is odd, if the degree of the polynomial is odd, then we know that p at x has at least one root. The reason why this is true is if you have a polynomial that's odd, then you know that, let's say as x gets infinitely large, that polynomial is tending towards positive infinity, then it must be the case that if x gets infinitely small, that polynomial must tend towards negative infinity. And therefore, since polynomials are continuous and there's no holes or breaks in the graph, it must be the case that these polynomials must meet. And for those two polynomials to meet, they must cross the x-axis. And that must be at least one root or one x-intercept to our polynomial. Also notice if the degree of a polynomial is even this time, then that polynomial must have an absolute maximum or absolute minimum value. Let's take a look at why. Let's say, for instance, that the polynomial p at x as x gets infinitely large tend towards positive infinity. Then it must be the case that the polynomial as x gets infinitely small must also tend towards positive infinity. And therefore, at some point along this curve, there must exist an absolute minimum value. So in this case here, that quick little graph I've drawn here, this is your absolute minimum value. And again, if the polynomial had n behaviors tending towards negative infinity, then we would have had an absolute maximum value, maybe that this drawing here would be up here. So the point being here is if you have a polynomial of even degree, then it'll have an absolute maximum or absolute minimum value. Let's now shift our attention over to the concept of turning points. The turning point of a graph is where the function goes from either the function is going from increasing to decreasing or from decreasing to increasing. And that would be considered a turning point. So in this example here, we've got a polynomial. You can see here we've got these 2 points here. These would both be turning points. This function has gone from increasing to decreasing, so we have a turning point. And then we go from decreasing to increasing, and we have another turning point. All right, let's look at another example. So for this example here, same idea. The function is going from increasing to decreasing, and then we have exactly one turning point here. So this polynomial here, you might notice this one here. This is the graph of y equals x cubed. Your function y equals x cubed, if you remember, is increasing. It's an increasing function. And by that I mean that as I read this from left to right, the entire domain of the function is getting larger and larger and larger. Therefore, this is an increasing function. Therefore, there's no point where the function goes from increasing to decreasing or decreasing to increasing. So this function has no turning points. Let's take a look at some useful properties regarding turning point. One fact of turning point is that for a polynomial that has degree n, let's say you've got a polynomial of degree n, that has at most n minus 1 turning points. So you have a polynomial of degree 5, it has at most 4 turning points. Polynomial of degree 12 will have at most 11 turning points. And in this example here, we can see this polynomial here has at most 2 turning points. So again, like we said, this has 0, 1, or 2 turning points. Notice here as x gets infinitely large, our polynomial p at x, examining this here, as x gets really, really large, this will still approach positive infinity. Multiplying by that negative 2 will make it tend towards negative infinity. And as x gets infinitely small, our polynomial in this case here, by cubing it, it's still going to go infinitely small, but then multiplying by negative 2 will shift that and make it tend towards positive infinity. So notice here right away, we've got our n behaviors. I know the turning points are 0, 1, and 2, and the degree of this is odd. And like we've already talked about, when the polynomial has degree that is odd, it's going to have at least one root. All right, let's take a look at the graph of this polynomial. So you can see here, this is the graph of the polynomial, and as you can see, it turns out it had actually had 2 turning points. And as we discussed, as x gets infinitely small, it tends towards positive infinity, and as we were talking about, as x gets infinitely large, it tends towards negative infinity. And it does cross the x-axis, and it has at least one root. Let's look at another example. So for this example here, again, you have a fourth degree polynomial. You can see as x gets infinitely large, this polynomial will tend towards positive infinity. As x gets infinitely small, this polynomial will also tend towards positive infinity. So now, since the degree of this polynomial is even, you can see it's of degree 4, it has an absolute minimum value. So again, when you have a polynomial that has n behaviors both equal to positive infinity, because it is a polynomial, there's no holes or breaks in the graph, so you must have a connection here between these two n behaviors, and there must be no holes or breaks like we're discussing. So because of that, there must be a minimum point, and therefore this has an absolute minimum as well. So even degree polynomial has an absolute minimum. The degree is 4, and therefore there's 0, 1, 2, or 3 turning points. Let's take a look at the actual graph and see what characteristics it has. So looking at the actual graph here, we can see we have a turning point here. So actually only has one turning point, and you'll notice here that as x gets infinitely large, both tend towards positive infinity, and it turns out that the turning point is the absolute minimum value. All right, that concludes today's lesson on turning points and n behaviors. Thank you.